This educational material is prepared by Dr. Nima Madian. Welcome to the Explainer, everyone. Today, we're diving into an absolute masterclass on Siemens S7 PLC hardware architecture. I'm going to walk you through every single critical component here. We'll go from the nuts and bolts of advanced addressing and memory organization all the way to complex system expansion and the exact steps for physical commissioning. So if you're looking to understand how to design and build these industrial powerhouses totally from the ground up, well, you are the exact right place. Let's get to it. Okay, let's just jump right in and look at the physical reality of an industrial control panel. Mastering this S7 architecture really requires a dual focus approach. You can't just be a software whiz, and you can't just be a hardware technician. It doesn't work that way. You've got to deeply understand the relationship between the digital brain, like how the PLC is actually processing memory, and the physical hardware layout sitting right there on the rack. The two are inextricably linked, and that's exactly what we're going to unpack today. Here's our game plan for this session. We're going to logically progress through 5 key areas. First, I/O process image mapping. Then, central rack anatomy and buses. After that, rack typology and specifications, followed by architecture scaling and expansion. And finally, we'll wrap up with the mechanical commissioning procedure.
So let's kick things off with Section 1, I/O process image mapping.
Now, when we're dealing with digital addresses here, they strictly use a byte.bit format. So, for example, I1.2 simply refers to input byte 1, bit 2. Pretty straightforward, right? But here is what's absolutely critical to remember. By default, a module's starting byte address is permanently tied to its physical slot number. So imagine you pop a 16-input digital module into slot 4. It's automatically going to occupy bytes 0 and 1. That gives you addresses 0.0 to 0.7 and 1.0 to 1.7. If you then place your next 16-input module right next to it in slot 5, it occupies bytes 4 and 5. Because of this strict default physical mapping, addresses in bytes 2 and 3 are just completely skipped over. They remain entirely unused, which creates this distinct gap in your address space. You can bypass this using user-defined addressing, sure, but you absolutely have to understand this default logic first. All right, what happens when we introduce analog modules? Well, we shift away from individual bits and move to the 16-bit conversion rule. Because analog quantities need 16-bit digital values, they actually consume 2 full bytes of memory per channel. And there's a really critical concept here called the input-output parity rule. Basically, the starting address for an analog module is exactly the same for both its inputs and its outputs. So, if an analog module in slot 4 has a default starting address of 256, the first input channel begins at 256. But here's the kicker. Any output channels on that exact same module will simultaneously begin at address 256 for the output process image. They share that identical starting point. Now, of course, not every single setup out there uses separate modular cards. If you're working with the compact CPUs, specifically the IFM series, things are handled just a little bit differently. These specific modules actually feature built-in, integrated digital and analog channels right on the CPU hardware itself. And because the hardware is integrated like that, it uses fixed, predefined addressing schemes. These are schemes you've essentially just got to memorize, or at least keep a reference chart handy when you're designing your logic. Just to make that a bit more concrete for you, let's look at some numbers. For the CPU IFM 312, its 10 digital inputs are hard-coded right to addresses 124.0 to 125.1, and its 6 outputs sit at 124.0 to 124.5. Now, if you step up to the slightly beefier CPU IFM 314, you get a larger array. You're looking at 20 digital inputs spanning 124.0 to 126.3 and 16 outputs going up to 125.7. The 314 also integrates analog channels. You get 4 analog inputs that occupy addresses 128 to 135 and 1 analog output sitting right at address 128. Being able to clearly visualize these exact address ranges is just non-negotiable before you sit down to program these specific CPUs. Moving right along, let's get into Section 2, Central Rack Anatomy and Buses. Okay, I want you to imagine looking directly behind the mounting plate of an S7 400 central rack. That underlying architecture actually serves 3 completely indispensable functions. First off, it's the structural backbone, using this really sturdy aluminum carrier rail with precise plastic guiding parts to hold everything together. Second, it provides the electrical infrastructure. We're talking robust local ground connections and pulling operating voltage directly from the power supply module, which, by the way, you'll almost always find anchored right there in slot 1. And third, it houses the I/O bus. That's a parallel bus embedded right into the backplane, explicitly designed for the super rapid, error-free exchange of those I/O signals we just talked about. Now, on this 18-slot rack, the I/O bus is actually physically divided into 2 distinct segments. You have slots 1 through 9, and then slots 10 through 18. But running straight across the bottom is a single, completely uninterrupted communication bus. Why does this matter? Well, this segmentation provides a massive, real-world architectural advantage known as multi-computing. It literally allows you to install two independent CPUs in a single rack. They can operate totally autonomously on their own specific I/O segments while still sharing a single power supply, a battery backup, and the ability to seamlessly transfer high-volume data across that shared serial communication bus. It's a really brilliant design. Which brings us to Section 3, Rack Typology and Specifications. Let's methodically break down the rack models here. The UR1 and UR2 are your universal racks, 18 and 9 slots respectively, and they contain both I/O and communication buses. Then you have the UR2H. That H stands for your fault-tolerant option, which is physically isolated into two sections to provide strict redundancy. The CR2, like we just saw, is the segmented central rack with that dual I/O bus, but a shared communication bus. And finally, we have the ER1 and ER2. These are your expansion racks. And the absolute key thing to remember about ER models is that they explicitly lack a communication bus. That is a massive distinction. In fact, I want to deliver this engineering note with the utmost emphasis, because missing this tiny detail will literally break your physical automation setup. As I just mentioned, the ER1 and ER2 strictly lack the communication bus. That means they do not support interrupts, period. Furthermore, any modules requiring a 24-volt DC supply from the backplane must receive it from an external supply when they are placed in these specific expansion racks. You can't just drop any old card into an ER and expect it to magically function exactly like a central rack. It won't happen.
Let's keep moving. Section 4, Architecture Scaling and Expansion.
So, how do we solve the problem of a central rack running completely out of physical slots? We deploy expansion racks using interface modules, or IMs. You basically install a send module in the central rack, which routes down to a receive module in the expansion rack. But of course, there are hard network limits in Dr. Mahadian's architecture rules. A single central rack supports a maximum of 4 parallel expansion chains. Each of those chains can then house up to 6 expansion racks. So if you do the math, this strictly caps your network at an absolute maximum of 21 expansion racks per central rack. And here's another crucial rule. Every single one of those ERs requires a unique hardware identification number set via tiny dip switches right on the receive IM. If you accidentally have duplicate numbers on the same network, it will cause a total system failure. Now, the specific type of interface module you choose completely dictates your system topology. Let's look at setup A. This uses the IM 460-1 and 461-1. This is strictly for close distance setups, limited to a 1.5 meter radius. Why so short? Because it's actually physically transmitting a 5-volt power supply directly to the expansion racks, up to a massive 5 amps. Now, in stark contrast, look at setup D. This setup uses the IM 464 and 461-4 for long-distance remote transfer. It does not transfer power and it does not transfer the communication bus, but the trade-off is that it can span an absolutely incredible distance of 605 meters. These module limits dictate the entire physical scale of your factory floor. Visually trace the lines here. A chain utilizing that IM 460-1 transfers that 5-volt local power, but again, it caps out fast at just 1.5 meters from the central rack. Contrast that with a chain using the IM 460-4. It scales outward through multiple expansion racks, all the way to that staggering maximum 605-meter length. It brilliantly illustrates just how flexible, yet strictly regulated, the S7 expansion network really is in practice. All right, let's bring all this theory back into the real physical world with Section 5, Mechanical Commissioning Procedure. Commissioning a module isn't just plugging something in. It requires precise physical mechanics. Before a single piece of hardware is manipulated by your hands, the CPU key switch must be explicitly set and completely isolated in the stop position. You never, ever install or remove hardware while the CPU is actively running in run mode. Safety and hardware integrity are the absolute non-negotiable prerequisites here. Let's drill in the 4 exact mechanical steps for commissioning a module. Step 1. Safety isolation. You visually verify the CPU is in stop mode. Step 2. Rail engagement. You securely hook the top notch of the module directly into the upper aluminum mounting rail. Step 3. Seating the bus. You swing the module firmly downward until the rear connectors rest completely flush against the backplane signal bus. And step 4, which is incredibly critical, torque fastening. You must fasten the mounting screws at the bottom strictly between 0.8 and 1.1 newton meters. If you over-tighten it, you're going to crack the housing. If you under-tighten it, you'll eventually cause a bus fault due to machine vibration. We have journeyed all the way from the abstract bit-level memory mapping right down to the exact physical torque required on a single module screw. As we've seen today, a single error in default addressing or failing to realize an ER rack lacks a communication bus can literally halt an entire industrial process. So I want to leave you with this question. How will you apply Dr. Madion's exact engineering rules to design and scale your next fault-tolerant automation system? Thank you so much for joining this explainer, and I really look forward to seeing how you implement these critical hardware architectures out in the real world.